Decades-old quantum spin liquid puzzle resolved physicists have resolved a long-standing problem in condensed matter physics by experimentally confirming the existence of emergent photon-like excitations in a three-dimensional quantum spin liquid. The discovery provides direct evidence for a true quantum spin ice, a highly entangled magnetic state that had remained largely theoretical for decades, and establishes a new experimental platform for studying emergent gauge fields in solid-state systems. If you like my content and want to listen more interesting science stories like this, then subscribe my channel. And don't forget to like and share this video with your friends and colleagues. In work reported in Nature Physics, an international research team led by Pengcheng of Rice University identified both emergent photons and fractionalized spin excitations in the crystalline material cerium zirconium oxide, Ce₂Zr₂O₇. These observations confirm that the material realizes a clean three-dimensional quantum spin liquid resolving persistent ambiguities that had plagued earlier candidate systems. What makes quantum spin liquids unusual? Conventional magnetic materials develop ordered patterns as they are cooled, with atomic magnetic moments aligning in regular arrangements. Quantum spin liquids behave very differently. Even at temperatures near absolute zero, their magnetic moments do not freeze into an ordered state. Instead, strong quantum fluctuations keep the spins dynamically correlated, producing a highly entangled ground state. In certain quantum spin liquids, specifically quantum spin ice, the collective behavior of spins can be described by an emergent form of electrodynamics. Theoretical models predict the appearance of photon-like excitations and fractionalized particles known as spinons, which carry spin but not electric charge. Until now, direct experimental confirmation of these predictions in three dimensions had remained elusive. Direct detection of emergent excitations. The Rice-led team overcame this challenge using polarized neutron scattering, a powerful technique that allows researchers to selectively probe magnetic fluctuations while suppressing background signals. This capability proved essential for detecting the subtle signatures of emergent excitations at very low energies and temperatures. The measurements revealed a low-energy continuum consistent with photon-like modes predicted by quantum spin ice theory. These excitations exhibit a linear dispersion relation, analogous to the way sound waves propagate through a solid, a hallmark feature of emergent gauge fields. Complementary specific heat measurements further supported this interpretation, showing behavior consistent with the presence of gapless emergent photons. Crucially, the experiments also identified spinons, fractionalized excitations that serve as sources and sinks of the emergent gauge field, providing a complete set of signatures expected for a three-dimensional quantum spin ice. Resolving a long-standing debate. Previous experimental efforts to identify quantum spin ice behavior were often compromised by material disorder, extrinsic magnetic effects, or limited experimental resolution. In contrast, Ce₂Zr₂O₇ exhibits minimal structural imperfections, allowing its intrinsic quantum behavior to be observed with unprecedented clarity. Combined with advances in neutron instrumentation and sample quality, this enabled the unambiguous identification of the predicted excitations. As Dye noted, the direct detection of these modes answers a central question in the field: whether quantum spin ice can exist as a genuine three-dimensional phase of matter rather than a fragile or approximate realization. Broader implications. The confirmation of emergent photons and spinons in a real material has significant implications for both fundamental physics and future technologies. Quantum spin liquids provide a rare opportunity to study emergent gauge theories in a laboratory setting, offering insights relevant to high-energy physics and quantum information science. Beyond their conceptual importance, such materials may eventually support applications in quantum computing and low-loss energy transport, as their excitations are protected by the collective nature of the quantum state. By validating decades of theoretical work, this study establishes Ce₂Zr₂O₇ as a benchmark system for exploring deeply entangled quantum matter and opens a new chapter in the experimental study of emergent phenomena in